talk about Cascode amplifiers today. Over this weekend, I don't know if it's going to be one homework assignment or two homework assignments. Probably going to be two, one on current mirrors and all of that kind of stuff, one on Cascode things and all of that kind of good stuff. Because I'm going to be hitting you with two at once, I'm going to make sure that there's enough time to actually do the two at once and all that kind of jazz. I'm also going to try to get off my lazy butt and get your design problems and all of that kind of stuff in, because I want you to knock one out before we get into frequency response stuff, which will be happening shortly after we get back from the Easter holiday, I believe. All right, so Cascode amplifiers. So we're going to start by looking at a BJT Cascode amplifier. We are going to use NPN transistors for this, but we could turn it upside down, as it were, to do an PNP if we were so inclined. So we are going to start with a representation where we are using a current source to bias things. So this is our bias current source. Here's VCC. And then down here is where we're going to hit our transistors. So at this node is where we're going to take our output voltage. Down here will be our ground. We're going to call this transistor Q1 and this transistor Q2. We are going to apply a DC bias voltage to the base of Q1. And then we are going to apply our input signal that we're trying to amplify, as well as a DC bias voltage, to amplifier Q1. Okay. So effectively what we have here is two amplifier stages kind of stacked on top of each other. It's not going to work exactly like as if we were cascading them like we did with amplifiers in circuits 2, which is part of the reason why this has a different name, Cascode. The other reason is because we are cascoding transistors or stacking them on top of each other like we saw with our current source the other day. So if we were to just worry about what I put in this green box right here, what would this kind of look like? To me, it looks like a common emitter amplifier. I haven't explicitly stated that my output voltage for this transistor amplifier is up here, but I don't know where else it could be, because the other pin is at ground and the other pin is our input signal. So we have something approaching a common emitter stage here. And then up here, if we take our input signal to be supplied from that common emitter stage on bottom, what type of amplifier would that part be? Common base, right? So we have the common base stage effectively stacked on top of a common emitter stage, and we call this a Cascode amplifier. For our small signal model, which we're going to be looking at in detail here, let's go ahead and kind of draw that out. So I'm going to start with my common emitter stage down here on the bottom. So here I have my input voltage signal. Here's my base transistor 1. My resistance R pi 1, my base emitter voltage VBE1, GM1, VBE1 in parallel with R0 This is my collector for transistor 1. Down here in the center is my emitter for transistor 1, which is grounded. Now, on top of this guy, I'm going to draw my small signal model for transistor 2. That'll be okay. This will be R pi 2, VBE2. Here's my base of transistor 2, which is at an AC ground. GM2, VBE2, R02. I'm going to tie these together. So effectively, the emitter of transistor 2 is tied to the collector of transistor 1. Here's my collector for transistor 2. Here's my output voltage. And then because I'm choosing to represent this as current source bias, everything beyond that is just an open circuit. So that's going to allow us to figure out how just this part of things work. And then later on, we'll see what happens when we connect transistor current sources up above, where realistically, that's just going to look like some finite resistance. Okay. All right, so this is our small signal model. We're going to approach things in a different order than we have been doing it. Usually we calculated our voltage gain first, then our small signal input resistance, and then our small signal output resistance. Also, I don't know why none of the other monitors are on. Do you guys need those, or are we good with just this and it being recorded? Okay, because I don't particularly want to troubleshoot shit, but I will if I have to. All right, anyway, got distracted. And then lastly, we're going to figure out our small signal voltage gain. And the reason why we're doing it last is because we're going to use the short circuit transconductance method to figure things out. Because as you might be able to surmise just by looking at this thing, finding our voltage gain directly for this particular topology is a huge pain in the butt because our output's way up there, our input's way down here, and we got so many different things going on that the short circuit transconductance method will be much easier. So with that in mind, let's determine our input resistance. So as much as you guys hate this, I'm going to make a copy of this small signal model and just use that. Put it right about here. And I'm just going to change this Vn to be a Vx as if it were a test source. Here's my test current Ix that we're looking for. And I no longer particularly care about my output voltage, so I'm just going to remove that node because that's not really what we're interested in here. So as every other case that we've looked at, our ultimate goal here is to simply find the ratio of Vx to Ix. So we can see an easy thing or two here for the input resistance. I think that our input resistance Rn, defined to be the ratio of Vx over Ix, should be fairly trivial here, right? Vx is Vx. Ix is quite obviously the current flowing through our resistor R pi 1. So I could say then that that's going to be simply VBE1 divided by R pi 1. Well, what's the relationship between VBE1 and the X? They are literally the same thing. So that's going to look like Vx over R pi 1. And so our input resistance just comes out to be R pi 1, exactly the same as if we had a simple common emitter amplifier with no degenerations. John, how may I help you?
Sorry, what is the second B?
X.
No other, they're both BX?
Yes.
Okay.
So input resistance, real easy. Okay. Now let's figure out our output resistance. Once again, I'm just going to use that copy of my small signal model and then adapt it to my needs. So in this case, since we're finding our output resistance, my test source is going to be applied across the output terminals of my amplifier circuit. So here's my Vx. Here's my Ix. And I need to turn off my input voltage. So I'm going to ground this guy right here. And what can we observe here? The bottom circuit is literally just R01. So just to be extraordinarily clear about that, VBE1 must be 0 because both the base and the emitter of transistor 1 are grounded, which means that GM VBE1 must also be 0 amps or an open circuit. So all we have down here is a resistor R01. Absolutely correct. So what about VBE2? Okay, let's figure that out. I'm going to tuck it down here where we're going to do the math or explain things. But let's look at things really quickly here. So this resistor R01 classically is defined between the node C1 and the node E1, right? So the collector of transistor 1 and the emitter of transistor 1. However, the collector of transistor 1 is tied to the emitter of transistor 2, and the emitter of transistor 1 is at ground. So to me, that resistance R01 appears as if it is in parallel with the resistance R pi 2, because they're both between emitter 2 and ground. Are we okay with that? Okay. So we could effectively eliminate this whole bottom part right here with this change. Everybody okay with that? So now defining VBE2 should be, I think, significantly easier. What I mean by that explicitly is we can see our current Ix is going to flow into the collector 2 node. It's going to divide between that R02 resistance as well as that dependent current source, and then it's going to add back together and flow through that parallel combination of R01 and R pi 2. Anybody got beef with that? Okay. So we can say that VBE2 is simply negative Ix times R01 in parallel with R pi 2. Now we can use Kirchhoff's voltage law around this path. This is extraordinarily similar to a path that I drew explaining a homework problem the other day. So starting here at this ground, going across Vx, going across resistor R02, going across these resistors, and ending at this ground over here. Okay, so starting from ground, ending at ground, this is a perfectly valid Kirchhoff's voltage law path. Applying KVL, what we would see is that our voltage Vx is going to be equal to the voltage drop across resistor R02. So that's just going to be R02 times the current flowing through R02. And I'm going to choose to express that current as Ix minus GM2 VBE2. We all okay with that? And then the next thing I see is the negative polarity terminal of voltage VBE2. So I'm going to put a minus VBE2 here like so. And now I can just do simple substitution. So Vx is going to look like R02 times Ix plus Ix times GM2 R01 in parallel with R pi 2 plus Ix times R01 in parallel with R pi 2. Anybody have an issue with the substitution that I've made, signs, algebra, all that jazz, where I usually make dumb simple mistakes? Everything seems legit. Okay. Our output resistance should then be the ratio of Vx to Ix, which is going to look like R02 times 1 plus R01 in parallel with R pi 2. So just to be clear here, I took care of this term. I've taken care of this term. Now I'm going to give us the term in the middle. That's going to be GM2 R02 times R01 in parallel with R pi 2, which should be approximately equal to GM2 R02 times R01 in parallel with R pi 2. Meaning the expectation is that that third term is significantly larger than R01 in parallel with R pi 2 by itself, which is very obvious because it's GM2 times R02 larger. And we're expecting that the term is also larger than R02, which should be obvious because it's GM2 times R01 in parallel with R pi 2 times larger. So 90-ish% of the time, we should be able to assume that we can throw those two resistors away. But if we want to be very formal, we could just do the whole thing. All right, so input resistance, fairly straightforward. Output resistance, a little bit trickier, but realistically, it's damn near the exact same thing as stuff that we've done before. Looks incredibly similar to an amplifier with a degeneration resistor because that's kind of what it is. Now let's figure out our voltage gain. And to figure out our voltage gain, we are going to have to figure out what our short circuit transconductance is, right? Or we're not going to have to, but that's the method that I'm going to choose to employ because it's significantly less of a pain in the butt. Right. So this is the first time that we're doing this where we don't have an expected answer, right? And on Wednesday's class meeting, when we applied this approach, we compared it to calculating the voltage gain of that, I think it was a common base amplifier directly. And we found out that it worked, but here we don't have that safety net. So let's be very meticulous about what we're doing so that we understand exactly what's going on. So anytime I'm trying to find the short circuit voltage gain, I'm short circuiting my output terminal. I'm finding the current flowing out of ground, or the current that's flowing into the output terminal, if you will. And then my short circuit transconductance is simply the ratio of my output current divided by my input voltage. So let's see what shakes out of this because our output terminal is now grounded. Okay, so my resistor R02 is connected between emitter 2 and ground. My resistance R pi 2 is connected between emitter 2 and ground. My resistance R naught 1 is connected between emitter 2 and ground. So really R naught 1, R naught 2, and R pi 2 appear as if they are all connected in parallel. Are we okay with that? Okay. The voltage VBE2 is the voltage seen between ground and the emitter 2 node. So I could redraw this circuit as follows, where this will arguably be a little less gross to look at. So here's VN. Here's R pi 1, VBE 1, here's my node E1, my node B1. Over here on this side, I have GM1, VBE1. Give myself plenty of room for all those resistors in parallel. This is going to look like R naught 1 in parallel with R naught 2 in parallel with R pi 2. This is my voltage VBE2. Here's GM VBE2. For what it's worth, this node is the collector of 1 and the emitter of 2. And here's my output. So does anybody have any questions about this representation? Or does anything not make sense? Let's start there. Yes, Nick.
Can you explain again why R naught 1, R naught 2, and R pi 2 are all in the middle now?
Absolutely. So all three of those resistances are connected to this node in orange, right? So one terminal is all at that node in orange. The other terminal for R pi 2 is at ground. The other terminal for R naught 2 is at ground. The other terminal for R naught 1 is at ground. So they're all between that orange node and ground. So they're all in parallel. So I'm choosing not to treat that as a resistance currently, effectively, is all that I'm doing. Like, because my base and collector aren't truly diode connected, I'm leaving that where it is. Like, they're essentially diode connected, but I don't actually have it wired up that way. I'm choosing to leave that current source up top there just to see what shakes out. It's going to wind up making the math a little bit easier by treating it that way, as opposed to just putting a fourth resistance thing down here and having to sort what shakes out of it. So it's a little esoteric because I'm choosing to do it this way, but that's why I'm doing it that way. Yes.
How did you decide that the three resistors, like, put the others? Just, you know that that's what's gonna make the math better, or is there kind of a system? If you move the R by 2 and R not 2 to where R not is.
Right.
But how did you decide that?
Because I could observe that I out is just going to be GM VBE2 if I draw it this way.
So it's just what's gonna make my next step easier.
Yes, 100%. So, as I mentioned just a moment ago, I out is going to be GM2 VBE2. That's simply Kirchhoff's current law. Current flowing into that very top node has to equal the current flowing down out of that very top node. Nothing particular wild or crazy there. And we can see that, let's see, if we apply, let's see, no, that's exactly what I did just there. So I out is equal to GM2 VBE2. And applying KCL, we could say that GM VBE2 is going to be equal to this current flowing out and this current flowing out, right? So that's going to be equal to GM1 VBE1 minus VBE2 divided by R01 in parallel with R02 in parallel with R pi 2. Okay. All of that is from Kirchhoff's current law. Anybody got any questions, comments, or concerns here before we start doing substitutions? Okay, so a couple of things here. I can see very easily that VBE1 is just Vn. And I can see very easily that VBE2 is just I out over GM2. Looking at that relationship right there. So if I substitute those relationships in what I want into my top equation, what I'm going to wind up getting is that I out is equal to GM1 Vn minus I out over GM2 times R01 in parallel with R02 in parallel with R pi 2. And then I can move that I out term to the other side.
How are we relating GM2 VBE2 to GM1 VN?
I'm literally just, yep, okay. So when I move the I out term to the other side, I get I out times 1 plus 1 over GM2 R naught 1 in parallel with R naught 2 in parallel with R pi 2 is equal to GM1 times Vn. Now what I'm going to do, and you'll see why I'm going to do this in a moment, is I'm effectively going to express that thing that's being multiplied by I out as a single fraction as opposed to 1 plus a fraction by lumping everything together with a single common denominator. Okay. So that's going to give me I out times 1 plus GM2 R naught 1 in parallel with R naught 2 in parallel with R pi 2, all divided by GM2 times R naught 1 in parallel with R naught 2 in parallel with R pi 2 is equal to GM1 times Vn. And from this, my short circuit transconductance I out over Vn is just GM1 times the reciprocal of that thing. So GM2 over R naught 1 in parallel with R naught 2 in parallel with R pi 2 divided by 1 plus GM2 times R naught 1 in parallel with R naught 2 in parallel with R pi 2. All right, so let's look at this really quickly here. Formally, this is fine. Not too god-awful to deal with. R naught 1 and R naught 2 are both typically larger than R pi 2. They're not crazy larger than R pi 2 by any stretch of the imagination, but they're usually larger. So let's just say, for the sake of argument, that I was able to reduce this parallel combination of resistors down to R pi 2 by itself. What would this numerator look like? GM2 times R pi 2, which would be beta. Realistically, it'll be a little bit less than beta, but somewhere in the ballpark of beta. So I have GM1 times close to beta over close to beta plus 1. For large beta, what's that look like? About 1. So we just did a ton of work to prove that the short circuit transconductance of this big ugly combination is going to be about GM1. So from this, our voltage gain, negative GM times R out, becomes negative GM1 times R naught 2 plus R naught 1 in parallel with R pi 2 plus GM2 R naught 2 R naught 1 in parallel with R pi 2, or approximately negative GM1 GM2 R naught 2 R naught 1 in parallel with R pi 2. And if transistors Q1 and Q2 were matched, this comes out to be negative GM squared R naught times R naught in parallel with R pi. So how does this gain compare to that of a simple common emitter amplifier with a current source load or current source bias? So that should have a gain of negative GM R naught. So this is GM times R naught in parallel with R pi, larger in gain, right? So let's compare the performance of the cascode amplifier here qualitatively, and then we'll do a little bit of math to show how it looks with numbers and all of that kind of good stuff. So compared to a common emitter amplifier, our input resistance is the same, right? Our output resistance is significantly larger because this thing right here is inherently significantly larger than R naught 1 would ever be. Okay. Our voltage gain is also significantly higher. Okay. So if we want a lot of gain, this is the ticket. Or actually, let me rephrase that. If we want a lot of gain with effectively the same performance as a common emitter amplifier, this is the ticket. It fulfills the role of a common emitter amplifier in very high gain circuits. Okay. So let's say that we are calculating the gain for the following two circuits where our collector current IC is 1 milliamp, beta is equal to 100, and our early effect voltage is a paltry 5 volts. I say that because realistically, it would usually be much larger than that, resulting in a much larger R naught. Okay. And our two circuits are simply a current source biased common emitter amplifier Yep. Yeah. And well, actually, a small R naught is going to make us not be able to use that assumption. A large R naught is what's going to allow us to make our assumption. Now, we're going to use it anyway, but I'm just showing. Good question. You kind of caught me on my bullshit here. We're going to make the assumption for our short circuit transconductance being approximately GM1 either way, just to show you what shakes out. But the results of this would actually be more, we would see a larger difference if VA were larger. Yeah. Yes. Similar input resistance and output resistance. So what I mean by that specifically is these transistor amplifiers, or the single transistor amplifiers in particular, and now also the cascode amplifier, are building blocks for analog integrated circuits. So they're going to be parts of larger things. And we are literally just going to be like, all right, we're gonna drop this box in here because we need this role to be performed for this stage of whatever's going on. So that's why I'm looking at overall performance, and by that I mean specifically input resistance, output resistance, and voltage gain. So that when we are constructing large-scale analog integrated circuits, we're putting in parts that we know fulfill those specific criteria needs for that part of the overall system. Does that make sense?
You're saying we're building building.
Yeah, exactly right. So this is a red Lego and the other ones are blue and orange Lego or some such nonsense. Yeah. I guess I should have said something more intelligent than that, since the color of Legos means literally nothing regarding their efficacy as a building block. But yeah. So all right, so assuming that all of our transistors are the same transistors, meaning they're all matched, our transconductance IC over VT should come out to be 38.462 millisiemens. Our R pi value, which is just beta over GM, would come out to be 2.6 kiloohms. And our R naught value, which is just our early voltage VA divided by IC, comes out to be 5 kiloohms. Our voltage gain for our common emitter amplifier, so I'm just saying AVCE, is simply negative GM R naught, which would be negative 192.308 volts per volt based on these parameters. Pretty respectable gain, almost 200. For our cascode, where we're going to use negative GM squared R naught times R naught in parallel with R pi, if we substituted in our numbers, we would get negative 12,651.822 volts per volts approximate. Or about 66 times larger. So a significant boost in voltage gain. Yes.
So if we want to capture more, do we have to rewrite the equation?
For sure, but also there are diminishing returns to this. And let me explain what I mean explicitly by that, okay? So we're looking at all of this stuff on a small signal level, right? Large signal, every transistor that we stack on top is another DC voltage that we have to make sure keeps that transistor operating in, for these VJTs, the forward active region, which means we need a VCE greater than the VBE that's biasing it and all of that kind of good stuff. So we get larger voltage gains, but we also eliminate headroom and we increase the probability that our gain is so high that it's going to actually push the device down into not the active mode of operation during at least part of its swing. So we can't just say, let's put 75 transistors up like this, and then we'll have the best amplifier ever, because it's like, no, you'll actually just have a really shitty DC voltage source. Because it can't do anything but effectively just give you VCC at the output. All right, so in practice, we can't actually make an ideal current source. So instead, we're going to wind up loading this thing with a transistor current source. So I'm going to draw a picture here, and I'm intentionally going to put a blank in it. So this box right here represents a transistor current source. This Q1, Q2. Here's where we're going to take our output voltage. So my question to you guys is, what do we want to put in that box? And I'm not asking for anything super specific here, but what considerations should we take into account, right? And so let's contextualize that by thinking about our voltage gain in particular, okay? So for our Cascade amplifier, we know that our voltage gain is negative GM times a resistance R out. And we found that the resistance R out looking down, which I'm just going to call R down, was equal to, let me find it here in my notes. R02 plus R01 in parallel with R pi 2 plus GM2 R02 times R01 in parallel with R pi 2. And we could approximate this if we were so inclined as GM2 R02 R01 in parallel with R pi 2, right? That's our resistance looking down. This is typically really large, right? If we put, so we have a couple of different things that we could do here. Let's say that we just put a resistor RC there. Fixed value resistor, typically on the order of a couple of kiloohms. Why would that be a bad idea? Why? So what do you mean by taking, well, I'm not sure what you mean by taking away some of the voltage drop. You're right that it's a bad idea and that it's going to reduce the gain. This is the resistance we see looking down from this node headed towards ground. The resistance that we see looking up towards AC ground is RC. So whatever we put up there is going to be in parallel with this resistance. So if we don't put something large, we're killing our voltage gain because R out is small, right? So putting just a resistor there is terrible. Putting a single transistor there, like a single transistor current source, is better than putting just a resistor, but it's still pretty bad. Realistically, we need to put a cascoded something there in order to maintain our very high voltage gain of this circuit, right? So for simplicity's sake, we might put a cascode PNP transistor current source, where let's call this Q3, this Q4, V bias 4, V bias 3, and now the resistance seen looking up is going to be approximately GM3 R03 times R04 in parallel with R pi 3. So something comparable to the resistance that we see looking down, so that our voltage gain would only be half of what it would be in an ideal case, right? Where the ideal case is we literally have an ideal current source bias in this thing. So just as a slightly different perspective for analyzing circuits, and we've kind of sort of been doing this already. Our output resistance is always effectively just going to be whatever we see looking up towards AC ground in parallel with whatever we see looking down towards AC ground from the output node, which, like I said, we haven't explicitly done, but if you go back to some of my approaches where I'm just like, oh, well, this thing's in parallel, so we're just going to tuck it in later, that is exactly what I was doing. All right. We've got 20 minutes left. Let's knock out MOSFET cascodes in a tight 5 minutes and then call it a day. Yes. So if we put a large resistor there, we are going to have a large voltage drop over it if it's carrying a current, right? So let's say, for example, this VTC for 5 minutes. If we put a physical resistor there, and let's say also, just for the sake of argument, that the current flowing down through here is on the order of half a milliampere, right? Or that's what we're trying to have happen to give us a good transconductance value, large value for R naught, all that kind of good stuff. What's 5 volts over half a milliamp? 10 kilo ohms, right? Which means if we put a 10 kilo ohm resistor in it, all of our transistors below it are off because there's literally no voltage from here down affected. All of that couldn't actually be on if we were able to actually drive half a milliamp through that 10 kilo ohm resistor. So putting physical resistors is we're never gonna actually be able to put a large enough resistor to it without forcing all of these transistors either very deep into saturation or worst case scenario. Yeah. That's the beauty of the small signal resistance of a transistor. Is that it's a small signal resistance, not a large signal resistance. Whereas a physical resistor exhibits the exact same resistance in both our large signal model and our small signal model, which means we get large DC voltage drops across them, eating up all of our headroom. We're talking about specifically integrated circuit type things where we don't have the luxury of using, 36-volt power supplies and all of that kind of jazz. Okay, MOSFET cascade. So unsurprisingly, it's going to be the exact same thing as a BJT cascade, except that all of the transistors are replaced with MOSFETs. Or all of the BJTs are replaced with MOSFETs. So we might have something like this, where I'm just going to go ahead and put in the cascade current source here up top. So this will be M4, M3, bias 4, bias 3. The out. M2, M1, bias 2. Sorry, that should be VN. My apologies. Our resistance looking up will be approximately GM3, R0 3, R0 4, since R pi is infinity. Actually, R0 3 plus R0 4 plus GM3, R0 3, R0 4 should be the exact value, which will look like just GM3, R0 3, R0 4, since that's typically going to be much larger than R0 3 and R0 4 by itself. And then down, we would see pretty much the exact same thing, except that I put up instead of down. Let's see, R0 1 plus R0 2 plus GM2, R0 1, R0 2, and shouldn't take any stretch of the imagination to realize that our short circuit transconductance is going to look approximately like GM1. Let's just scroll back up here really quickly to kind of explain why. So now this is no longer looking like a beta because it doesn't really, beta doesn't exist. So we have GM2 times R0 1 in parallel with R0 2. If those transistors are matched, that's effectively just 1/2 GM2 times R0 over 1 plus 1/2 GM2 times R0. Again, it's still something that's very close to something a little bit smaller than what's below it. So it's going to look about like 1. Yes. No. Very, very good question. So let me prove why in just a moment. Okay. fantastic question. So over here, GM is approximately going to be equal to GM1, right? And so putting these things together, we should be able to figure out what our voltage gain is. All right, now let me answer Mr. Simpson's question. Small signal. Short circuit transconductance. I short my output mode. AC ground or VDD is at AC ground. And so this resistance can't contribute anything because it's shorted on both sides. So fantastic question, will not make any impact whatsoever. Small signal. So putting these things together, we are going to have approximately GM1 times GM2 R01 R02 in parallel with GM3 R03 R04. And obviously more formally, we could put these in if we wanted to. Okay. Shouldn't make much of a difference. One interesting thing about a MOSFET cascode is, particularly in integrated circuit design, we don't have access to really changing, you know, mu n, Cox, and all of that kind of good stuff, but we have the ability to change our aspect ratios, which in turn can change our transconductance and all of those kind of good things. Our transconductance are, if we had a really long transistor, we would have a lower channel length modulation coefficient and all of that kind of good stuff. So for BJTs, it's very obvious to say, well, as an integrated circuit thing, practically everything is going to be matched. For a MOSFET, we have to physically do that ourselves. So you may not have everything's nice and matched, and so paying attention to the subscripts kind of match. All right, that's cascode amplifiers. Yes. Oh, thank you. Yes, because it's negative GM RF. 100% correct.